Thank you very much. We okay? Sound check? Good. Okay. Yeah, well, thanks for that introduction, and it's a pleasure to be here. I'm usually talking at meteorology or satellite conferences, and it's good to branch out to another, discipline. Although, as this discussion will go, you will see that many of our products, obviously, the users are outside the discipline that we have. So. Let me just give a couple opening thoughts, and a few of the earlier speakers had, talked about, well, then it's not like NASA and satellite data. Well, what I do is like NASA and satellite data. And there's a quote from Bryson Keller, CIO Weather Channel, that just said weather is the original big data problem. I think that's right. It was one of the first uses of the ENIAC in the 1950s. And since then, there's been three trends in three general areas that have led to improvement in weather and climate modeling, and that is in the observing systems. That's probably where I've spent the bulk of my career. It's one of the core competencies of AER. Physical models, which are weather forecast models, but other models, and you'll see some, I'll give some insight into some other applications we have for flood mapping, which I think could be considered a physical model. And of course, information technology. The latest generation of every computer, one of the first applications is weather forecasting, weather and climate forecasting. So, and although everyone complains about the quality of the weather forecasts, I think objectively when you look, they've continuously improved over the 60 years, and there's no reason to believe that trend's not going to stop, and it's because of this, development in these three major areas. So I'm going to give a brief survey of what I call the weather economy value chain and talk a little bit about the mixture of just how this works and also the niches. This is, as you know, I think as you're aware, it is a system that is probably dominated by government, but not exclusively. Private companies are important, like the mention of the GOES-R satellite. Obviously, the government doesn't build these systems themselves. They put out to industry to buy them, so that's one thing. But also there's commercial products, but they got to fill in the niches of the government space filled by the economy. And but that is changing over time, and I'll give a little insight into what we've done and maybe some thoughts about where things may be going. So why don't we start? We're going counterclockwise, so I guess we're in the southern hemisphere now. And we'll start at the bottom left, the global observing system and the corresponding first-level processing of that data. So that's like what the GOES-R satellite is. It's going to be a major improvement over the current satellite, over 60 times the data volume, which is both twice the resolution, about 6 times the spatial temporal refresh, and about 5 times the number of channels. So it's pretty dramatic increase in data volume, and of course it drives the processing of the data. So first and foremost, those data, and those systems are fielded. It's an international system worldwide, of course, and then international. Europe is the other major developer of these satellite observing systems. And, but there are starting to be evolved some niches, I'll talk about that in a bit, for maybe private industry to provide this global observing system data. Then in the weather forecast models, the current state of the art is what we call ensemble forecasting. And you don't run the model once, you run it many times. The Europeans run it 50 times, the US runs their global model 20 times. And that allows people, it's a stochastic chaotic system. So that allows one to start to make statistical judgments about the data. I'll talk a little bit about one of our products built around that. So far, the global models have been dominated by, global forecast models have been dominated by government. The leading and best quality model is produced by the Europe ECMWF, that you probably have heard it mentioned on television, and it has maintained an edge for 20 years over the US model. And with some consternation in the U.S. The U.S. is in the middle of a major upgrade, continuing upgrade. They just had one probably, but the Europeans also upgraded their system. They'll probably still be better. Maybe in 3 or 4 years, there's going to be the next upgrade. Maybe the U.S. can start to approach them in quality. But they're all good. They're all better. Everyone's model is better than anyone could do 5 or 10 years ago, but it always pays to be first. And I'll talk a little bit about how that comes. Within the models, there's 3 key things, and AER plays in every one of these areas. There's data assimilation. You just can't take the raw data that you observe and just say, well, it told me the temperature is X here. Weather models are highly physically based, and the slightest imbalance, imprecision in those models can cause a totally busted forecast. They've had they can trace a single hurricane misforecast. There's been cases where they've found one bad observation has caused that. So the data assimilation system is very key. AER staff have been have helped advance this technology, largely under contract with either NOAA or the National Center for Atmospheric Research over the past couple decades. There's the dynamical core. This runs the Navier-Stokes equations, the actual hydrodynamic flow, and then there's the physics. That runs all the other stuff that happens, precipitation, the atmospheric radiation, and all those things. And AER researchers have done this. For example, AER has developed the radiative transfer models for that are running the world-leading models, including the European model, by the way. Okay, so then you get the raw model output data. Often this needs to be supplemented by auxiliary models, say a sea ice model. These can be coupled either loosely or tightly to the model. And then you need statistical post-processing. So in the statistical post-processing, the data come out, they're kind of in model space, may not exactly match the space of the, or practice has shown the grid point closest to Detroit does not necessarily give the most accurate forecast, so you apply physical or statistical post-processing. The other thing you often do here is downscaling. In fact, one of our forecast products provides, we take hurricane models also produced by the U.S., and then we downscale that data. That data is provided about 15 kilometers. We downscale that data to 1 kilometer and are able to give very accurate forecasts for the maximum winds, wind gusts, a whole host of parameters that are done. So this is a mixture of and very specific physical and statistical post-processing. Everyone sees the forecaster on television, and then there's also the guy in the back room at the National Weather Center, National Weather Service field offices, and but there's some hints that maybe AI forecasters will be on the out there. For example, IBM is starting to apply Watson. It can beat Ken James. Maybe it can beat the forecasters at the WFOs, and that's coming. Then there's what I call industry-tailored models, decision support systems, decision aids, and other kind of industry-specific, and we also play in that space. So, and then, of course, you need to distribute the data. So you can see in each one of these areas, and I'll talk a little bit about the technology trends, big data is obviously going to influence it. This ensemble forecast system, we want to get more ensembles, we want to get higher resolution, and the technology for, I spoke initially about global forecasts. The other forecast domain that's particularly important for the U.S. is regional forecasts that couple to severe weather. And in those, you want to run what they call a rapid update cycle. You want to rerun the model. Right now, they run it every, and the U.S. model here is quite good. You want to run that model right now they run it every hour. NOAA has objectives to start to run those models much more frequently and at a higher resolution, up to 1 kilometer. Right now, they're a little better than 10 kilometers. And the goal is to be able to run them very frequently and enable them to extend the warning time for tornadoes from about 10 to 14 minutes now to 30 to 60 minutes in the future. At 10 to 14 minutes, it's basically what we call a nowcast problem. You kind of see in the radar what's happening to the initial signs of a tornado, and then you send the warning out. To go to the half hour to more, you need to go into forecast mode. The models aren't there yet. They might be there in the 2020s. And that's going to require improvements in the models, improvements in the satellite observations. The GOES-R satellite's one important one, and they're going to also have to improve the radar systems. So what are some of the trends that are affecting us? Cloud computing, very important, and what I call frictionless data access. If you go back to the 1990s, a typical project we would do, you would spend probably over half on a lot of projects just getting the data in, having to put on tapes, mailed from one place to another. The ability to process and reprocess that data was very simple. Now the data are available on internet and increasingly in cloud-based services, and I'll talk a little bit about some NOAA initiatives there. And then also cloud computing, which is now turning computing into a commodity. You can start to reduce the cost of your IT department and, and really reap the benefits of Moore's Law that have been happening, without all the hassles. The Internet of Things is also very important. And, as I say, in the future, everything will be seen, tracked, measured, and connected. And, in the weather area, a couple of things we see there are, telematics, which is outfitting cars with instrumentation, and also, one of our partners, Harris Corporation, has a system called Helios that takes, right now they're starting with video cameras on trucks using machine vision techniques and determining the weather. So this is one thing. It's one example. These have not yet, I think, had a measurable impact on the weather forecasts themselves. But if we extrapolate ahead 10 years, it's hard to predict which ones will pay off and which ones won't. But yeah, I think it's safe to say that will happen. I don't have to mention Moore's Law. We all hope it doesn't end. It's been a great run while it's happened. But one of the things the Moore's Law is doing is, as I mentioned, the weather forecasts, particularly the global domain forecast, are dominated by the government. Regional forecasts, there's niche players that can do regional forecasts. Those software are open source. Anyone can run them. But at least until very recently, the ability to run a high-quality, state-of-the-art global model has really only been captured by governments, and most notably the U.S. Europeans. Canadians run a pretty good model as well. And then the Navy plays in that. So those are probably the top 4 models. And I'll talk a little bit later about what I see are some opportunities or emerging entrants into the global weather forecast model. And then reducing costs of sensor satellites and launch. If you follow budgets, maybe you'll question whether they're actually reducing, but they probably are, except for a few problematic programs if you measure it on the quality per bit or the overall data. But the Silicon Valley is starting to move into the satellite space, and there's some very real opportunities for commercial space observations. The key technology they call CubeSats, it's kind of a modularization of satellites, and CubeSats have been around for a while. There's some there's some novel sensing techniques that are out there. And so, we see that this all playing with Okay, so I'm going to give a brief survey and then have some concluding remarks, but of 3 products that kind of that play into this. One is what we call the African Risk Capacity Flood product. I'll talk about an ensemble weather forecast post-processing value-added product, and then a regional greenhouse gas monitoring system called Greenlight. Okay, so this is a project a colleague of mine led, John Glanowitz at AER. And it was for the African Union. It was sponsored and funded by the UN, and it was to develop a flood extent depiction product for the African Union to support a insurance product that they wanted to provide to their customers. The idea was to have a very objective and clear way to define the extent and both the extent and magnitude of a flood event to all their member states, and to be able to turn this information around. There wouldn't be weeks of surveys and calls and plane flights. They wanted to have a standard product available every day that tells you where it's flooded, where it isn't, and then in a very objective method to provide that flood data. There was a tender released, and AAR responded and won that. They had, John and his team came up with a very innovative approach to provide that, and we just delivered that product, and it's now operational as of a month ago. So, the idea is to provide data that provides 3 arcsecond, which is about 90-meter data over the whole African continent of flood extent. And we went back, but for an insurance product, you need historical data. We also need the historical data for quality control. So we got a set of data going back for 24 years, analyzed that data, provided a benchmark of this. We did the quality control. We can quantify the accuracy and both the success and limitations of the data, and have delivered that. Let me just walk through a little bit the flood extent risk quantification, the idea is we take the AER product, the flood extent, look at the population, we take a temporal mask, we then model the impact. AER does the one on the left, and then the ARC project does the one on the right, and then we can quantify the risk, and then the payments they start to disperse the payments right away. This makes a very big difference for them rather than getting the data. Will they get it? It's also very objective, so it takes a lot of politics out of it. So I'll just jump ahead. Like a lot of things, and this is kind of what we do, we look at novel, interesting techniques. I'll describe the problem here very briefly, which is the only good way to get daily observations of floods is microwave data. But the problem is microwave data is 20 or more kilometers in 10, 20 or more kilometers in resolution. Not good enough for this application. But the idea is we can take that high-resolution terrain data and then downscale that data and downscale it all to 90 meters. So this is an example of a short animation here. Shows a flood extent in Ghana in 2015. On the left is the very low resolution flood fraction. On the right, we're able to provide that data. So you can provide that data exactly. So this is kind of space AER works in, is to take a problem, we understand the physical limitations of what we know, and then can apply it to solve a particular problem. So I'm going to skip the takeaways. I think I mentioned most of them. Let me just make sure I touch on at least one of the other two areas. I may run out of time before that, and that is I'll talk a little bit about a value-added industry-tailored forecast product that this is AER's first entree to the commercial space. I led the launch of that product in the early 2000s called eCast. We take the ensemble forecast global data distributed by the Europeans and the U.S. We got to pay for the Europeans. The U.S. gives theirs away for free, which is interesting. We apply AER developed statistical post-processing. We use common filters. We actually have to run over 6,000, tune and adapt and model 6,000 common filters for this data. And then we distribute and display this data for users. They come to us and say, what do I do? Turns out, our most demanding customers are energy traders. What do they demand? They demand very quick forecasts. At one time, we were fighting with our competitors over 15 and 20 seconds. Your competitors gave the data 15 seconds earlier than you. Can you beat that? I think we eventually won, but that was quite a battle, and it's very important to them to get the data sooner. This is, and they need to see the data very quickly, so we designed some dashboards for them. I'll be wrapping up in just a second. And then also, as I mentioned there, ensemble forecasting, start to give error bounds on the data. Okay, so we'll skip the takeaways. I'll just give an overview, real quick thing as I wrap up. Because it mentioned climate, I wanted to mention one thing we're doing with climate at AER, and that's with Greenlight, which is uses tomographic techniques to measure regional greenhouse gas distribution. Ultimately, we want to put this technology in space. We're trying to find the right opportunity, but for now we're demonstrating on the ground. And in this thing, at the bottom right are the actual laser sources. The others are retroreflectors. You choose your wavelength right, and then you scan sequentially through all of those retroreflectors. You're able to determine the path, the concentration of carbon dioxide, and we're expanding that to methane and other gases right now. We've done this with our partner, Harris Corporation, and provide real-time data. This was installed in Paris in last fall for the COP21 conference as a demonstration. And you can see this is evolution of Paris over the course of a day. We've gone through, we're still in the development stages with this, but we've done validation with in situ data, and it's very, very promising technology, and hopefully we're going to be able to put this into space. So let me just close out with a couple perspectives and just takeaways here. One is the weather and climate business is thoroughly grounded in physics. Statistics is important, but as I like to say, the statistic starts where the physics ends. So we take the physics as far as it'll get us, we apply the statistics, and that's example of all of our products like ECAS. We apply statistics at the end. We use the input data. The reduction in computing costs is going to have very significant things. And government policies, we're starting to see some traditionally market industry only participate in regional forecasting, and again, the same energy community would want those high-resolution data. There were certain things that the government data didn't provide, but we're now, there's a Panasonic has started trying to market a global forecast model. We'll see how that goes. It's a very recent launch, but when there's one market entrant, I expect more, and that's going to be interesting, and there's a lot of ways to compete. Just like we competed by providing the data sooner, maybe they provide data that's as good on average, but sooner than the government forecasts, and might be able to compete with industry that way. So there's a lot of ways to find a competitive edge. And then these other technologies I had. So I want to thank you for your participation. I'm interested in answering any questions you may have during the panel discussion.